Okay, number 4. So this one is about the centralizer of an element A, right? So let's say you have a group and a certain element A. If your group is not abelian, then it's not the case that everybody commutes with everybody, and it's not the case that everybody commutes with A. But some people commute with A, right? I shouldn't say people, some elements commute with A. And so those elements that commute with A are called the centralizer of A. And it turns out that it's a subgroup, right? It's not merely a set, it's actually a group by itself. So let's prove that that's the case. So first of all, we got to prove that the subset, that this subset is closed. So we'll start by letting these two things be in the centralizer, right? And what does that mean? Well, it says it right up here, right? What it means to be in that set is that you commute with A. So we know that X star A is the same as A star X. And we also know that Y star A is the same as A star Y, right? Because that's the meaning of them being in the centralizer. And then what we want to show is that X star Y is in the centralizer, which is to say that X star Y commutes with A, right? So we want to show that X star Y star A is the same as A star X star Y. And it's not so hard if you know that X and Y both commute with A. Check it out. The way that I like to do it is, we're in an associative group here, so parentheses don't matter. You don't have to write parentheses. You can just write things out. You can just be like this. Well, boom. Y is in the centralizer, so I can just swap those two and call this X star A star Y. And then same deal. X is in the centralizer, so I can just swap those. Aha, look at that. So it turns out, So it turns out that X star Y also commutes with A, which is exactly what it means for X star Y to be in the centralizer of A, right? So there we go. So we picked any two random elements of the centralizer, and it turns out their product is also in the centralizer, so that means it's closed. Okay, what about the identity? Is the identity in the centralizer? Well, yeah, right, this basic action, does the identity commute with A? And it sure does. The identity times A is the same as A times the identity, because both of those are just A. So, boom. Right, because that's what it means to be the centralizer, is that your product with A in both directions are the same. And then finally, what about inverses? Right, so we pick a random element of the centralizer. So we know that X times A is the same as A times X. And we got to prove that that same thing is true for X inverse, right? Well, it is, right? Because check it out. We can take this equation and multiply both sides on the left by X inverse. So if we multiply on the left by X inverse and do the same thing on this side, the point of doing that is these cancel out because they're inverses of each other. So we just get the much nicer equation. Like that. Well, not much nicer actually, but we're a little bit closer because we've got an X prime now instead of an X. And then we'll do the same thing for the other one, right? We'll just multiply, we'll just give it a times X on the right, times X inverse on the right. That way it cancels out over here, just like it canceled out over there. And so we get X star X prime equals X prime star A. And hey, that's exactly what it means for X prime to be in the centralizer, right? So it turns out that X prime is in the centralizer. So we just proved that it's closed, that the identity is in there, and also it's closed under inverses too. So that is what it means for CA to be a subgroup. So the centralizer of A is not only a subset, it is actually a subgroup. Okay, so now for part B, Does the group CA have to be abelian? So this is one that almost everybody got wrong. No, it does not. The centralizer does not have to be abelian. So things in the centralizer merely have to commute with A, but they don't have to commute with each other, right? There's a special element of the centralizer A, which everybody commutes with, but that doesn't mean that everybody commutes with everybody. It's just everybody commutes with A. So if you'll notice, as we were doing this part, nowhere did we swap the order of X and Y, right? Because X and Y might not commute with each other. The only thing we know is that they both commute with A, you know? So to see an example of when this would not be abelian, consider your favorite non-abelian group, right? So whatever non-abelian group you really like. I really like the dihedral groups, like I said. So you could pick that, or if you want to be more bigger, you could talk about, matrices. And then consider CE, right? So what if you just took the centralizer of the identity? Well, who commutes with the identity? Everybody. So the centralizer of the identity is actually the entire group. So if this is non-abelian, well, then your centralizer around E anyway is non-abelian because they're actually the same. So the point is, no, it's not always the case that the centralizer is abelian. This is just saying everybody commutes with E, or if that was a different thing, everybody commutes with that one element, but not everybody necessarily commutes with each other. So no, the centralizer does not have to be abelian.